Mass rate of flow of an ideal gas through an isentropic nozzle. We now consider the mass rate of flow per unit area m dot A. Mass rate of flow m dot A in a nozzle from the continuity equation. M dot A PV on R T PV on radical KRT T0 on T which is also equals to by substituting into the equation. The flow per unit area can be expressed in terms of stagnation pressure, stagnation temperature, Mach number, and gas properties. M dot on A multiply to M square at the truth M equals to 1. Then we can write this relation. M dot on A star The area ratio A on A star, area ratio A star where the area of truth. The area ratio A on A star is the ratio of area of the point where the Mach number is m to the area that to the truth area. M related to R, M equals to related to R star truth. Yeah. As a function of Mach number, this figure shows a plot of A on A star and Mach number, which is the accordance with our previous conception that a subsonic nozzle is convergent and supersonic nozzle is diverging. The final point to be made regarding the isentropic flow of an ideal gas through the nozzle involving the effect of variable back pressure on the mass rate of flow. This picture shows that this is the Mach number equal to 1 with the Mach number converging, diverging, converging. A convergent nozzle, consider a convergent nozzle as shown in this picture, which have a back effect of back pressure. Consider first a convergent nozzle as shown in this picture, which also shows the pressure ratio P on P0 along the length of the nozzle. The pressure at the exit plane of the nozzle is designated by PE and the back pressure is designated by PB in the picture. Let us consider how the mass rate of flow m dot and the exit plane pressure PE on P0 varies. PE on P0 and m dot. These quantities are plotted in this picture. When PB on P0 equals to this point, PB on P0 equals to 0 and PE on P equals to 1, 0 and 1, PE on P0 equals to 1. As designated by point A, next the back pressure PB be lower to that designated by point B so that PB on P0 is greater than the critical pressure. The mass rate of flow has a certain value of PE on equals to B. The exit Mach number is less than 1. Next, the back pressure be lowered to the critical pressure designated by point C. The Mach number at the exit is now unity and PE is equals to PB. When PB is decreased below the critical pressure designated by point D, there is no further increase in the mass rate of flow. PE remains constant at the value equals to the critical pressure and the exit Mach number is unity. The drop in pressure from PE to PB take place outside the nozzle exit. Under this condition, the nozzle is said to be choked, which means outside the nozzle exit. Under this condition, the nozzle said to be choked, which means that for given stagnation condition, the nozzle is passing the maximum possible mass flow rate. This point, the maximum possible mass flow rate. Consider next a divergent nozzle in a similar figure here. Point A designated the condition when PB equals P0 and there is no flow. When PB is decreased to the pressure indicated by point B so that PB on P0 is less than 1 but considerably greater than the critical pressure ratio. Therefore, the diverging section acts as a subsonic diffuser in which the pressure increases and the velocity decreases. Point C designated the back pressure at which M equals to 1 here at the truth, but the diverging section acts as a subsonic diffuser in which the pressure increases and velocity decreases. Point D designated one other back pressure that permits isentropic flow, and in this case the diverging section acts as a supersonic nozzle with a decrease in pressure and an increase in velocity. Between the back pressure designated by point C and D, an isentropic solution is not possible and shock wave will be present. This matter is discussed in the section that follows. When the back pressure is decreased below that designated by D, as shown in the picture, the exit plane pressure PE remains constant and the drop in pressure from PE to P takes place outside the nozzle. This is designated by point E. Normal shock in an ideal gas flowing through a nozzle is an